Hello everyone, my name is Adrian Chua and I'm a student majoring in Mechatronics Engineering at UOW Malaysia KDU Penang University College. Today, for this competition, I'll be presenting my final year project, which is titled as Design and Development of a Modular Omnidirectional Robot for Task Execution and Locomotion with an Electromagnetic Coupling Mechanism. First, I would like to introduce a little bit about my project, where the robot that I've created is named as Tri-Omni. Basically, Tri-Omni is a modular omnidirectional tank robot that is designed for factory environments to replace manual tools like pallet jacks and forklifts. It features tank tracks for omnidirectional movement, line following navigation, and a QR code based task execution system. It also has an electromagnetic coupling mechanism that enables cargo towing, while ultrasonic sensors that is installed 360 degrees can enhance safety by detecting obstacles. Additionally, modular attachments allow for cleaning tasks, where it is a versatile and efficient solution for smart factories. You may be wondering, what is the problem statement for my project? Basically, conventional cargo handling tools like pallet jacks or forklifts are labor intensive, where most of them are manual labor and are very prone to error. They also lack adaptability in tight or changing factory layouts, meaning that it would need very large factory floor layouts for them to operate in. Besides that, fixed configuration robots also struggle with maneuverability, task versatility and precision, especially when hauling heavy loads. In order for them to overcome this limitation, the robot will need an omnidirectional movement. Besides that, they also need a reliable coupling mechanism for secure electromagnetic towing, an efficient control algorithm for line following navigation, and a QR code based station identification. Besides that, the robot will also need strong sensor integration, including compass module and ultrasonic sensor. This will ensure safety, stability and reliability, making the system adaptable to dynamic industrial environments. To further support why it is a good idea to implement this robot in a factory-based environment, this is a case study conducted by an organization called as OSHA, where this is conducted in the United States. This study shows the forklift related accident statistics, where in this study, 22% is caused by forklifts overturned, 20% caused by pedestrians struck by forklifts, another 16% where pedestrians are crushed by forklifts, 9% where there are objects falls from forklifts, and 33% where the forklift possesses other dangers. This shows that automated and advanced robotics can help to reduce this risk and also improving workplace safety and efficiency. This is the overall design of the Tri-Omni robot that I have designed in SolidWorks. It took me approximately 2 to 3 weeks to design the entire structure from the ground up. Basically, there are 3 main layers to this robot, where the first layer comprises of Locomotion system and 2 motor driver. The reason why we need 2 motor drivers is that because we have 3 motors in this system, where each motor driver can support up to 2 motors. For the second layer, it mainly comprises of the microcontroller, such as Arduino Mega, sensors such as ultrasonic sensor, switches, and a step-up buck converter. For the third layer, it is basically a battery compartment, where it will house a 3-cell LiPo battery and 4 18650 batteries. Back to the design of the Locomotion system. Basically, all of the parts that are designed for this robot are modular, meaning that if one particular part is broken or missing, you can just change that part without having to change the entire thing very easily. Furthermore, because that the design of the robot is a triangular design, only one of the sides will be used for towing purposes, meaning that for that triangular design, 2 of the Locomotion system will be identical, which is shown in the left photo. The left and the right photo is the exact same Locomotion system, where the only difference is that the right one has a electromagnetic holder in it. The Locomotion system comprises of sprockets, pulley that will move the sprockets, which is pulled by the motor, and 4 bearings to ensure smoother of the locomotion system. For the right locomotion system, it comprises of electromagnetic and limit switch to let the robot knows that when it is already towing an item. In order to provide movement for the robot, the sprockets of the locomotion system will be used to propulse this tank track. The tank track shows here is an individual piece where most of it will be linked together using PLA filament into a chain-like shape. The mini wheel here shown in red color is a TPU material where it is similar to a rubber material to provide more grip for the robot to move in, no matter that it's moving at tiles or cardboard or rough areas. This picture shows the internal wiring of the robot, where this is the second layer that comprises of the microcontroller and other various sensors. From this picture, you can see that most of the wires are secured permanently using cable tie, where most of the wires routing are routed under the microcontroller instead of over the microcontroller. This is to prevent the wire from getting loose and also have a more permanent connection with the microcontroller and the sensors. To print these designs into life, a 3D printer is used to print these parts using a material called ABS, where it is more robust compared to PLA. The video here shows a time-lapse of one of the parts that are printed by the 3D printer here. For the third layer, which is the battery compartment mentioned earlier, the battery compartment is held using magnets, where you can just change the batteries very easily, and there is also an OLED display above where it is connected using magnetic pins as well. The omnidirectional movement of the robot is made possible by its design, where it is shaped as an equilateral triangle. When it wants to move horizontally to the right, both of the right motors will move at the same motor speed at the same direction, where the third one will move in the opposite direction at 50% motor speed. When it wants to move forward, two of the motors will move in the same speed, where this applies for reversing as well, where the motor will move in the opposite direction at the same speed. When it wants to move in a clockwise rotation movement logic, all of the motors will move in the same direction at the same motor speed. In order to show the functionality of the robot, a very simple game field is constructed at the campus, where it has a length of approximately 410 cm and a width of 476 cm. It has two stations, which is station A and station B, and a cargo bay where the robot will haul cargoes from. The video attached here shows the robot delivering a cargo from the cargo bay to station Alpha autonomously. First, the operator will have to input a QR code telling the robot which cargo and which destination that they want the robot to go to. The robot will then align itself to the cargo using compass and attaches the cargo using Electromagnetic. The robot will then show its omnidirectional capability, where it is able to move in tight spaces. This is a line following logic for the robot to move. It will then stop at an intersection to check whether this is the intersection that it wants to turn in using the QR code. From here, it will autonomously detaches the cargo and go back to its home position, which is the cargo bay. Once it has arrived at its home position, it will turn around and align, and then waits for another input from the operator. This video shows the robot delivering cargo from the cargo bay to station B, where it is the same operation as the station A. When the robot arrives at the junction, it will scan whether this is the junction that it wants to turn in, and it will match to its initial QR code. It will then automatically detaches the cargo and go back to its home position. Besides hauling cargo using its electromagnet, it can also attach modular devices such as a cleaning attachment, as shown here, where it will go into cleaning mode, that you attach a cleaning device such as a mop or vacuum behind it, and it will move around the production floor or a factory to clean the entire floor. To show that the line following logic for this robot is stable, meaning that the robot is able to find back the line even though it's going off course, I've introduced some kicks or pushes to make it off course, and it is able to find back the line autonomously. There are 4 main SDGs applied for this project. The first one is SDG 8, which is decent work and economic growth. This robot enhances workplace efficiency by automating manual cargo handling. It also reduces labor-intensive tasks and minimizing workplace accidents. The second SDG, which is SDG 9, Industry, Innovation and Infrastructure. This project supports smart factory automation with advanced robotics. It also improves productivity, safety and adaptability in industrial environments. The third SDG is Sustainable Cities and Communities. The project promotes safer and more efficient logistics in urban industries, which reduce reliance on conventional forklifts that contribute to workplace hazards. For the last SDG, which is SDG 12, Respond, Consumption and Production. This project also encourages sustainable manufacturing by using modular and reusable components, which reduce waste in and automation solutions. That is all for my project. Thank you very much, and if you guys like it, please show some support. Thank you.